Hi guys, welcome back. We're going to solve some pendulum problems now. So this should go along with the note packet you guys have. So for a pendulum, and this is going to be for small angles. Remember we made those approximations that this only works for small angles. The period depends both on the string length, which will be measured from a fixed point to the center of mass, and the acceleration due to gravity, what planet you are on, and again, for physics, our favorite way to make you be on a different planet is to accelerate you in an elevator. And so our formula is that the period, capital T, P, is equal to 2 pi square root L over G, where this is our acceleration due to gravity of the planet. All right, so a pendulum has a period of 18 seconds. How long is its string? So I want to get L by itself. I'm going to divide by 2 pi. I'm going to square both sides and multiply by G. And so this is going to be 10 meters per second squared times 18 seconds squared divided by 4 divided by pi squared. So that is one long pendulum, 82 meters. All right, the length of a pendulum with a period of t is doubled. What is the new period? All right, so looking at our formula, I don't have to move anything around because that's our formula already. Change, what gets changed? L is going from 1 to 2. G is staying at 1. Our 2 and our pi aren't changing, so I would still put in 1s for those, and it changes by radical 2t. A simple pendulum consists of a 1 kilogram brass bob on a string about 1 meter long. It has a period of 2 seconds. The pendulum would have a period of 1 second if. All right, so I want my period to go down to a half. I don't have a choice to replace the 2 or the pi or the G. So what would give me a half underneath that radical would be a quarter, right? The length of a quarter would give me a half. And so I would have to make my string go down to 0.25. And again, mass doesn't matter and amplitude doesn't matter. So really you could figure this out just by deciding that you'd have to have a shorter one to have a shorter period. A pendulum consists of a sphere suspended from a light string oscillating with a small angle with respect to the vertical. The sphere is then replaced by a new sphere of the same size but greater density and is set in oscillation with the same angle. How do the period, maximum kinetic energy, and maximum acceleration of a new pendulum compare to those of the original pendulum? So same angle, same length, same gravity, so the period's the same. So I can cross out those two lines. The maximum kinetic energy would just be mgy equals 1/2 mv squared. Well, the mass cancels out of that. Acceleration is related to the restoring force. The restoring force is mg sine of theta. The mass cancels out of that, so it is the same all along. It is the acceleration of a simple harmonic oscillator ever zero? Is the force on a simple harmonic oscillator ever zero? Yes, when F is zero. So in the case of a spring, it would be when the spring is neither being stretched nor compressed. It would have no acceleration. Real springs have mass. Will the true period and frequency be larger or smaller? Well, if I make that bigger, it's going to make the period larger. And then since frequency is 1 over period, it's going to make the frequency smaller. A mass on a spring in simple harmonic motion has an amplitude of A and a period T. At what point in motion is the velocity zero and the acceleration zero? And simultaneously, never. The acceleration is zero at a maximum velocity when there is no spring force. Object oscillates back and forth on the end of a spring, which the following statements are true at some time during the course of motion. The object can have zero velocity and simultaneously non-zero acceleration. That is true. So when it's at the rest, it has an acceleration because it has a net force. Second one's not true. The object can have zero acceleration and simultaneously non-zero velocity. That's true. So when it's not being stretched or compressed, when it's at the equilibrium position, that would be the case. Okay, so I have our mass spring system. I want to double the period. I want to get m by itself. So I'm going to have t squared over 2 pi equals m over k. And I'm going to multiply both sides by k. And then I'm going to change what they tell me to change. Everything else I'm going to put in for 1. So k is 1. They want the period to be doubled, so that's 2. 2 and pi are unchanged. That gives me 4. So my mass needs to be 4 times as much. The object of mass m rests on a frictionless surface and is attached to a horizontal ideal spring with a spring constant k. The system oscillates with an amplitude a. The oscillation frequency of the system can be increased. Okay, so that doesn't work. T is 2 pi m over k. So F is going to be 1 over 2 pi k over m. So if I want this to be bigger, I want k to be bigger, or I want m to be smaller. Because making the bottom of your fraction smaller would do that. And hopefully you can read these off the paper. Remember, these are in the notes. In an experiment with a simple pendulum, measurements of the period t of a pendulum are made for 4 different values of length L. When plotted on the graph, which of the following would result in a straight line fit of the data? So we want to look at how t and L are related to each other. T is directly proportional to radical L. So do I have a T and a radical L? I do not. But I do have a T squared and an L. So that would give us a linear relationship. A simple pendulum of length L, whose bob has a mass m, oscillates at period t. If the bob is replaced by one with 4 mass m, the period of oscillation is unchanged. Right? There's no mass in that formula. Like I said, they'll try to trick you up because some things make one thing change and some things make the other thing change and some things make both things change or don't make both things change. So long as the chord can be considered massless and the amplitude is small, the period does not depend on the mass.